So now we begin our discussion of set theory, and we're going to start off just with how we write sets and what are the basic operations we can do with them. So a set is just a collection of objects put inside to a pair of braces, and those different objects must be separated from one another by a comma. So for example, here we have a set, and it has three objects in it. So we see these braces. This tells us we're looking at a set. The three objects inside are 1, 3, and the letter A, and they've been separated by commas. The things that we put into a set are called elements of that set. So the set we have here has three elements, and they are the numbers 1 and 3 and the letter A. Now we have this symbol right here, and this can be used to construct statements about what is and isn't an element of a set. So we can write 3 is an element of the set containing 1, 3, and A, and that becomes a statement which is true. We could also write 5 is an element of the set containing 1, 3, and A, and that is a statement which is false. So this symbol, tells us we are making a statement, a claim, which is either true or false, about what is or isn't an element of a set. And as an aside, just want to point out that the symbol is written as a swoop like this and then a line. It is not written like this. This is actually a different symbol in math, and it means something else. So if you want to negate a statement about what is or isn't an element of a set, we just strike through that symbol. So for example, we can say 5 is not an element of the set containing 1, 3, and A. That is now a true statement. It is true that 5 is not an element of this set. Equivalently, you could write negation of, and then the entire statement, 5 is an element of the set. Similarly, you could write 3 is not an element of this set, and now that's a false statement, which is equivalent to the negation of 3 is an element of this set. In practice, you hardly ever see people write negation of statements about what is or isn't an element. You just use the symbol is not an element of. So, the universe. We're not actually moving into metaphysics or anything like that. Rather, the set of all things that could belong to sets in whatever sort of problem you're discussing is referred to as the universe. This is very similar to what was called the domain of discourse in logic. So in one setting, the universe might be letters of the alphabet because we're doing practice problems and we're making sets out of letters of the alphabet. In another problem, the universe might be all positive integers because we want to talk about sets of positive integers. So the universe is just the collection of things that are legitimate to put into sets. So you should either explicitly say what it is, or it should be very clear from whatever context you're working in what the universe is. It's always going to be denoted with the letter U. So a capital U always denotes the collection of all things that are allowed to be put into sets in whatever context we're talking about. And finally, we get to introduce something familiar, the equals sign. So two sets are said to be equal if they have exactly the same elements, regardless of what order they appear in, and even possibly being repeated. So here are several sets that are all equal to one another. What are the elements of this set here? 1, 3, and A. What are the elements here? While they appear in a different order, 1, 3, and A. And what about this set here? Well, the elements are 3, 3, 3, 1, 1, A, 1, A, 3, 3, 3, but overall, the elements were just 1, 3, and A. So these actually are all the same set. They are all equal to one another. However, these two sets are not equal because this set here contains 5 and this one doesn't. So these two sets do not contain exactly the same elements, so they are not equal. And we can write, much like we said, you can take the is an element sign and strike through it to negate those sorts of statements. We can now strike through the equal sign and say is not equal. Now this new symbol has 3 properties. First of all, any set has the same elements as itself. So a set is always equal to itself. If A and B have the same elements, then B and A have the same elements. So if A is equal to B, then B is equal to A. If A and B have the same elements and B and C have the same elements, then A and C must have had the same elements. Note we're actually making true or false statements here, and what we're claiming is for any set A, this statement is true. For any sets A and B, if this statement is true, then this statement is true. And for any sets A, B, and C, if both of these statements are true, then this one is. So really, we could have written this as a quantified statement where our domain of discourse is sets. So given any set A equals A is true. Given any sets A and B, notice this is now doubly quantified universally over sets A and B. If A equals B, then B equals A. And finally, given any three sets A, B, and C, if A equals B and B equals C, then A is equal to C. These are really the quantified predicate statements we're making over a domain of discourse, which is all sets. These are called the reflexive, symmetric, and transitive properties of the equals sign, respectively. Reflexive, because A reflects on itself here. Symmetric, because left versus right doesn't matter. And then this property here is called the transitive property. If A equals B and B equals C, then A equals C. Now, these are all properties that are true if we were talking about equality of numbers. But we're not talking about equality of numbers, we're talking about equality of sets, and the same properties are true for the equal sign here. One of the immediate uses of this new symbol is that we can now write sets using letters rather than always writing out things like braces and then listing all the elements by hand. So if I want to do some sort of work on a set, and I don't want to have to write it out in this long form every single time, I can just start off a problem by saying, okay, we're going to say that A is equal to this set as a given. And then I can write things about the set A, and I know what its elements are. It's 1, 3, and the letter lowercase a. And that way I don't have to continue to write this over and over and over again every time. Now we're going to talk about the principle of substitution. This is something that we did back when we were working in logic about replacing variables with other variables, right? So the equality sign combines with the principle of substitution through the following axiom. Okay, we got to take a pretty close look at this statement though. So this statement is quantified very differently than other ones we've looked at. So the universal quantifiers out on the left here are referring to sets. How do I know that x and y are supposed to be sets? Because here we have written x equals y, and equals is only something we know how to stick in between two sets. That's how we've talked about the equal sign, and that's the only way we've used it. So x and y are quantified over sets. But now look at this here. What is capital P? It's not exactly a set, because it's a predicate statement referring to sets. So here we're quantifying over sets, and here we're talking about predicate statements whose domain of discourse is sets. But what the principle of substitution here says is, if you have any two sets that are equal to one another, then no matter what predicate statement you form, P of x is logically equivalent to P of y. So if two sets are equal, any predicate statement you form, if it's true for one of them, then it's true for the other. And if it's false for one of them, then it's false for the other one. So two sets being equal means there's no predicate statement you can form that can tell the sets apart. Any predicate statement you form that talks about sets, if two sets are equal, one of them will be true means the other one is true, and one of them being false means the other one is false. Okay. So what's the big deal about having two different quantifiers that go over different things? We're not really going to go through this distinction, okay? And we're really just going to rely on this axiom intuitively, okay? It seems pretty obvious if two sets are equal, then anything I say about one of them, I can say about the other. And we're just taking it as an axiom that yes, if I can form a true statement about a set, and it's equal to another set, then that statement is still true regarding the other one. Okay, so there is no way to tell apart two sets if they are equal. What about restricted quantifiers? What does that mean? So there are two types of quantified statements that arise in talking about sets, and they come up all the time, and we use shorthand for them because they show up so often. So the first one is, it's very common to say the following: there is an x, so that x is an element of A, and something is true about x. Notice that this predicate statement is now talking about elements of sets, not sets. So there is an x which is in A and something else is true about it. This is something we're going to be saying a lot. And what we do is we abbreviate it like this. There is an x in A for which some particular statement is true. There is an element of x, there is an x which is an element of A such that P of x is true. And notice that's really what we set up here. There is an x which is in A and P of x is true. And now we're sort of massaging our notation a little bit and saying there is an x which is an element of A and P of x is true. This is just a very common way of writing it, but what it really is shorthand for all of this up here. Okay. This is something we're going to use commonly to say there is an element of a set for which some other thing is true. The other thing that comes up a whole lot is this. Given any x, if it is an element of A, then P of x is true. So for any element, if it is an element of A, then P of x. And here's how we're going to abbreviate that. Given any x in A, P of x. For any x which is an element of A, P of x is true. And again, this is just taking this collection of statements, which is actually a conditional statement, and writing it like this because it more naturally fits how we say things out loud. If we wanted to form a statement saying every element of A has some other property, that's really what this statement says. Everything in the universe, if it is in A, then it has this property. And we write it as anything in A has this property P. So the first one is used to say that there is an element of a set that has a property, and the second construction is used to say every element of a set has a particular property. Now let's talk about what are called truth sets. So the typical way that we're going to be constructing sets is through what, temporarily at least, we're going to call set builder notation. A set can be defined through a predicate statement as the set of all elements in a universe for which the statement is true. And we write it like this. A is defined to be or declared to be equal to a set, and now notice we're not listing things with commas anymore. This notation says the set of elements of the universe. We're always assuming we're talking in some sort of universe, so X has to be in the universe. So it's a set of things in the universe such that, that's what this vertical bar is sort of spoken as. So all elements of the universe such that P of X is true. So given a predicate statement, if I write this, what I've done is I've declared I'm talking about a set of elements of the universe such that the statement is true. This is called the truth set of the predicate statement P. Okay, it's the set of things in the universe where the statement was true. So consider the universe. In other words, the only things I'm allowed to put into sets, and the universe is 1, 2, 3, A, B, C. And then I form a predicate statement saying n of x is defined to be x is a number. Okay, so what are the elements of the universe where that statement is true? The elements of the universe, 1, 2, 3, A, B, C, for which the predicate statement, the thing is a number, is true, are 1, 2, and 3. So instead of listing out 1, 2, 3, we could write the set of elements such that n of x is true. What we're going to do now is talk about a whole bunch of operations and constructions on sets that are all actually defined as truth sets for certain predicate statements. However, many of them may already be familiar to you, but we're formalizing these notions as truth sets of certain predicate statements. The first thing we're going to discuss as a way of operating or constructing sets is unions. So if I have two sets A and B, the union of A and B is defined and notated as follows. we have A and then this symbol, which simply is spoken as union. The union of A and B is equal to the set. Now here, this notation says it's set builder notation, so it's all elements of the universe such that the following statement is true. X is an element of A, or X is an element of B. Now for this statement to be true, because it's a disjunction, either one of these statements being true is sufficient. Also note that we have a disjunction, which is like the letter V, but it opens upward, and we use for union this symbol, which also opens upward. So that is a way to visually notice that unions refer to disjunctions. So some quick examples. Here I have the set containing 1, 2, and 3, and here I have the set containing 3, 4, and 5. If I take their union, we're looking for things that are either in this set or in this set. Now, 1, 2, 3 belong to the set on the left, so these are elements for which the statement X is an element of this set will be true. 3, 4, 5 are elements for which being an element of the set on the right will be true. So overall, what are the elements for which either they are in the left set or they are in the right set? 1, 2, 3, 4, 5. Even though 3 is in both, that's fine. This disjunction will still be true. Here we've got the letters A, B, and the number 3, union, with A3 and V. A, B, and 3 will make is an element of the left set a true statement. A3 and V will make is an element of the right set a true statement. Here, the number 2 is a bit redundant. Okay, it's already in the left set, but still, all we do to take a union is ask, what are the things that are in the left set? Also, what are the things are in the right set? So here, they're completely what is called disjoint. They share no elements in common, so the union is formed by simply taking all of these, and there you go. Next up, intersections. So again, if we have two sets, we're going to define the intersection of them. Here's the notation. It's the same symbol, just turned upside down, because instead of talking about a disjunction, now we're talking about a conjunction. So the intersection of A and B is the set of all elements of the universe such that X is an element of A and X is an element of B. And again, the conjunction symbol opens downward like this, and so our intersection symbol also opens downward. This is a way to keep track of which is which. So, more examples. What are things that are elements of 1, 2, 3 and are also elements of 3, 4, 5? Well, the number 3 is the only thing that occurs on both sides. What are things that are elements of both AB3 and A3V? The letter A is an element of both. The number 3 is an element of both, and that's it. What are things that are in 2, 4, 6 and are also in 2? The number 2 is the only thing. This is an interesting one. What are things that are in 3, 4 and are also in 6, 7? There is nothing. So I make a set because I put the braces here, but I don't put any elements into it. There are no elements that are in this set and are also in this set. But that's okay. So we made a set that has no elements in it. We've never said we can't do that. So this is fine. Okay, because there is no obligation for a set to have any elements, we haven't actually done anything wrong by simply putting down a pair of braces and calling it a day. And we're going to come back and talk about this more. But now we're going to talk about something called subsets. So if I have two sets A and B, we say A is a subset of B, and the notation for that is this symbol here. It's like the same symbol for union and intersection, but turned sideways, and then it's got this little line underneath it. If the following happens, for anything in the universe, this conditional statement is true. If it's an element of A, then it's an element of B. So what we have done is not construct a new set. What we've done is we've made a statement about sets. So when we write A intersect B or A union B, we're talking about a new set. But if we write A is a subset of B, we have made a claim, a statement that is either true or false. So this is a fundamentally different sort of thing. We're making statements, not just building new sets. Now it's a conditional statement. So look at that underlying conditional statement behind the quantifier. This is true vacuously if x is not in A. If x is not in A, the hypothesis is false, which makes this conditional statement vacuously true. So look at the following claim. The set with no elements is a subset of B. That is true regardless of the set B, because if this is my set A, this hypothesis is always false because there is nothing in the set, so nothing is an element of it. So if this hypothesis is always false, then this conditional statement is always vacuously true, and then this overall is a true sentence. For any element of the universe, if it's in the set with no elements, then it's an element of B, is always vacuously true. So the set with no elements is always a subset of whatever I want. Suppose I have two sets and A is not a subset of B. Instead of writing this with a negation, we can just strike through the symbol. Okay, you'll notice that's basically what we do all the time. When we define a new symbol, if I want to negate it, we just strike through it, and that's much more common notation. What is worth pointing out is that saying A is not a subset of B is logically equivalent to the following mess here. Let's look back up here at the original definition of a subset and see why that's true. So suppose I have a negation plopped right out here. If I negate a universal quantifier, I can transform it into an existential quantifier on a negated statement. In other words, if I have the negation of all of this, that will be equivalent to the existential statement of this negation. But a false conditional statement is logically equivalent to a true hypothesis and a false conclusion. So if you have A is not a subset of B, that's equivalent to this, which is written right down here. So to say that A is not a subset of B is to say there is something in the universe that is in A and is not in B. So let's take a look at a bunch of claims and evaluate which are true and which are false. All right, so what we need to do is we need to ask, everything which is in the set on the left, is it also in the set on the right? If that's true, then the one on the left is a subset of the one on the right. If it's not true, then it isn't. So moving item by item. The first one is true. All we have to do is verify, is 1 an element of this set? Yes. Is 3? Yes. 5? Yes. 6? Yes. The fact that this set has something that isn't in the set on the left is irrelevant. All we ask to say is A a subset of B is, if it is in A, the one on the left, does that imply that it is in the one on the right? And that's true here. We don't have to be able to go the other direction. All right, is everything in this set also an element of this one? Yes. Is everything in this set also an element of this one? Yes. Is 2 an element of the set on the right? It is. Is 2 an element of the set on the right? It is. Is 2 an element of the set on the right? It is. Just because I repeated it 3 times doesn't mean that each one of these isn't an element of that set. They are. Okay, what about here? This one is now false. Is 1 an element of this set? Yes. 4? Yes. 5? Yes. 6? No. Also observe that I can talk about it with this construction here. There is something that is in the left set and is not in the right. 6 is in the set on the left and 6 is not in the set on the right. So the left set is not a subset of the right one. And what about here? False. 7 is in the set on the left and 7 does not appear anywhere in this set here. Returning to the notion of two sets being equal. Okay, so recall that two sets are equal if they have the same elements. In other words, every element of A is also an element of B, but also every element of B is an element of A. In other words, A equals B is logically equivalent to both of them being subsets of each other. A is a subset of B and B is a subset of A. In practice, if you want to show that two sets are equal, this is how you do it. You prove that one is a subset of the other, and then you prove it in the other direction. So if you can show every element of A is also an element of B, and every element of B is also an element of A, then you have shown that they have the same elements. This is referred to, by the way, as proof by mutual containment, if you ever see that language. So what you have to do is you prove two different conditional statements. They're very similar and they're related, but they are different statements. So a remark on subset notation is worth making here because notation varies slightly, and my notation is worth explaining. So this symbol that we've been using has this line underneath it. It's very common to see this symbol. So many places use this symbol for subsets, but sometimes, and this is less common, but it does happen, this symbol where that underline is missing specifically means A is a subset of B but is not equal to it. So in order to reduce confusion, we've just decided to use this symbol to represent A is a subset of B. It might be equal, but it might not be, but it is definitely a subset. So other sources will use this symbol to specifically mean A is a subset of B and it is not the same as B, but some other sources don't put that restriction in, and they use this notation for subsets even if they are equal, and then maybe they'll use this notation for when A is a subset of B and is specifically not equal. Because the notation varies slightly from place to place, in order to try to reduce confusion, I just use this symbol for subsets everywhere, and I don't have a separate symbol to specifically say is a subset and is not equal to. Okay, I only bring this up in case you are looking in other books or other sources online and you notice that the symbols are slightly different from place to place. You just have to be careful about it. So now we're going to talk about something called the empty set. Earlier, we constructed a set that has no elements in it, okay, and it was done as follows. So we give this set a special name. We call it the empty set, denoted with this symbol here. Notice that the number 0 does not have that strike through it. As soon as you put a strike through it like that, you're talking about something different, the empty set. So please do not use this symbol for the number 0. This set has a very special property, however. This set has no elements, so anytime I write something is an element of it, that's always going to be false, and if that's always false, it's a contradiction. So we can make the following claim. The empty set is a subset of A, and this doesn't matter what the set A is. Here's a two-column proof of that. Notice we started right out the gate with an assertion. Why did I write this as my assertion? Because that's the definition of the empty set is a subset of A. For anything in the universe, if it's an element of the set on the left, then it's an element of the set on the right. If I want to prove something about subsets, it's extremely necessary to know what the definition is, and here it is. Okay, this is just shorthand for this claim. So if you want to construct proofs in set theory, you need to know what the definition of all the various operators are. Remember, unions are a construction using a disjunction. Intersections are a construction using a conjunction. Being a subset is a universally quantified conditional statement. And all of these definitions are absolutely crucial to know. Okay, but anyway, moving on. Since we started with an assertion, we begin by assuming exactly the opposite. Once I see a negation of a universal quantifier, I can just pass the negation past by changing it to an existential quantifier. Now that I have an existentially quantified statement, I can instantiate it with a new variable that hasn't appeared anywhere, like lowercase a. A negated conditional statement is logically equivalent to a true hypothesis and a false conclusion, which I can then specialize by just pulling out this side here. But A is an element of the empty set is a contradiction. So having assumed the opposite of my assertion, I have derived a contradiction, which means the proof is complete. This statement was true even without any givens. Now this proof would apply to any set with no elements. So if B is a set with no elements, then B must be equal to the empty set, because the empty set is a subset of everything, but if B has no elements, it's a subset of everything as well. So if the empty set is a subset of B and B is a subset of the empty set, well then B is equal to the empty set. So any set that has no elements is equal to the empty set. This is why we don't call it an empty set, we call it the empty set. Any set with no elements is equal to this special set. So why talk about different versions of it? They are all the same thing, they are all equal. Okay, so that's why we call it the empty set. There's really only one empty set with no elements. And then one final term to introduce, if A intersect B equals the empty set. So if I have a set A and I have a set B, and then I construct their intersection by making a conjunction and asking, what are all the elements that are in A and are also in B? And I come up with nothing. There are no elements that are also in A and B. Then we say the sets are disjoint. So when I say two sets are disjoint, what I mean is the intersection is the empty set. So the next thing to discuss are called complements. If A is a set, then the complement of A, denoted A superscript C, is the set of all elements which are not in A. In other words, it's the set of all x's that are not in A. Now, in order to reasonably discuss complements of sets, we need to have the universe understood, because I need to know what is or isn't a legitimate thing to even try to put in the set A. So for example, if the universe is all real numbers, then the square root of 2 is not in the set 1, 2, 3, 4, 5. Therefore, it is in the complement. Okay, because it is a number, something in the universe, that is not in that set, then it does go into the complement. But if the universe was only integers, then root 2 is not even in the universe. Okay, even more to the point, bananas don't belong in the complement of this set because I didn't even really want to consider that as an element to put into a possibility. I mean, if you did, that's fine, but that's why the universe needs to be clearly understood. Okay, so the universe tells you what is even something possible to try to put into a set. And therefore, if you want to talk about things that are not in a set, in other words, complements, you need to know what's even legitimate to try. You need to have the universe declared before you can really talk about complements in a reasonable way. So suppose the universe is the digits 0 through 9. Then the complement of 3, 5, 7, 8, 9 is just all the digits that didn't appear, 0, 1, 2, 4, 6. And the complement of 0, 1, 2, 3, 6, 7, 8, 9 are the digits that didn't appear, 4 and 5. What's the complement of 4 and 5? 0, 1, 2, 3, 6, 7, 8, 9. What's the complement of 0 through 9? There are no digits that were missing, so the complement of that is the empty set. So it's true in general, in fact, that the complement of the universe is the empty set. Okay, if I'm only allowed to consider elements of the universe, and then I ask what are the things that are not in the universe, well, nothing. The complement of the empty set is also the universe. Okay, what are the things that are not in the empty set? Everything that I could possibly consider. In general, the complement of a complement is the set itself. Okay, what are the things that are not in a complement? What are the elements that are not in A? By double negation, those are the elements of A. Okay, we can also take differences of sets. So the set difference, which is not written with a minus sign, but this diagonal slash, okay? But we do call this A minus B. But it's not minus the little horizontal bar, it's this slash. Are those things that are elements of A and are not elements of B. So you take the things that are in A, but not in B. So it has to be in A and in the complement of B. So this has nothing to do, by the way, with subtraction in the sense of arithmetic, and we don't use the minus sign in order to not make that mistake. Okay. Set differences rely on complements, however. I mean, it's right there. Therefore, you need to know what the universe is before you can talk about set differences. So for example, we've got a universe and it's all the digits. What are things that are in 1, 4, 5, 6, 8, 9, but are not in 1, 5, 8? What are the elements of the set on the left and the complement of the set on the right intersected? So you take the set 1, 4, 5, 6, 8, 9, and you have to remove anything from 1, 5, 8. And if I take 1, 4, 5, 6, 8, 9, and I remove 1, 5, and 8, what's left behind is 4, 6, and 9. What if I have 1, 4, 5, 6, 8, 9, and I remove 1, 2, 3, 4, 5? Okay, now I have a 1 and I remove it, Taking away 2 doesn't do anything because 2 didn't appear in this set anyway. Similarly, taking away 3 doesn't do anything. But then I remove 4 and 5, and what's left behind are 6, 8, 9. If I have 1, 2, and 3, and I remove 1, 2, and 3, and 4 and 5, which does nothing, but I remove the element 1, I remove the element 2, I remove the element 3, I'm left with nothing, and the set with no elements we denote like this. Okay, ordered pairs. If I have 2 elements of the universe, you can put them in parentheses. Notice this is not a set. I didn't use braces, I used parentheses to make an ordered pair. So it's not a set. We didn't notate it like a set, and it's not going to be treated like one. It is something different. 2 ordered pairs are going to be called equal if and only if their first terms are the same and their second terms are the same. So now order matters. We distinguish which is first versus which is second. So the ordered pair 2, 3 is not the same as the ordered pair 3, 2. Were the first elements the same? No. Were the second elements the same? No. These are not the same ordered pair. Okay. Both elements of an ordered pair, by the way, can be the same as long as it's in the universe. You can make an ordered pair 2, 2, something like that. It's also worth pointing, you've already worked with these. Points in the plane. One real number, comma, another real number, where the first number is your x-coordinate and the second is your y-coordinate. Those are ordered pairs of real numbers, and it matters which is first versus which is second. The x-coordinate means something different than the y-coordinate. So we're taking that notation that you've already worked with, ordered pairs of numbers, and saying that they don't have to be numbers, they can come from any universe or any collection of sets that we are working with. They don't just have to be real numbers. All right, the next definition that we're throwing in this gigantic explosion of new terms is product sets. So if A and B are 2 sets, if I ask what are all possible ordered pairs made, something from the first set, comma, something from the second, that's the product set. So notice how we've denoted it here. The product of A and B is equal to the set of ordered pairs A, comma, B, where this statement is true. The first element was an element of the set A on the left, and the second element was an element of the set B on the right. So it's all possible ordered pairs, something from this, comma, something from that. So suppose we have 1, 2, 3, and 0, 1. We have to make all ordered pairs where the first element is either 1, 2, or 3, and the second element is either 0 or 1. So I go through this fairly mechanically, and I do 1, 0, 1, 1, 2, 0, 2, 1, 3, 0, 3, 1. And I've made all possible ordered pairs. The first element is either 1, 2, or 3. The second element is either 0 or 1. That's all there is to it. We're not multiplying anything. I happened to use numbers as the elements of these sets, but I could have used letters or other random symbols, and it wouldn't really matter. We're not actually doing any multiplication. Just like the difference of 2 sets did not actually involve any subtraction, we're not doing any multiplication. We're just making ordered pairs. Okay, almost done with our definition explosion. Power sets. If A is a set, we can make a set out of subsets of A. So we use this fancy script P and say the power set of A is a set whose elements are sets, things that are subsets of A. So unlike other sets that we've built, the elements of this set are actually not necessarily elements of the universe. Rather, they are other sets. And that's not a problem. I can put sets inside sets. Again, we never said we couldn't. So for example, A has 3 elements, 1, 2, and 3. Here's the power set. This is all possible subsets of A. The empty set is always a subset of anything. So anytime you make a power set, the empty set is a possible subset. The way I've gone about this is I've asked, let's make all possible subsets with no elements. Well, the only set with no element is the empty set. Let's make all possible subsets that have a single element. So maybe I take the set containing 1. Notice this is not the number 1. This is the set containing 1. This is a very common error. But elements of the power set have to be sets. This is a subset of A. This is also a set within A, a subset of A. And here I have another subset of A. These are the three possible subsets that have a single element that I can make out of the set A. So these three subsets are elements of the power set. And then I could go on and say, what are the subsets I can build that have two elements? I can make the set containing 1 and 2, the set containing 1 and 3, or the set containing 2 and 3. And then what about subsets containing 3 elements? Well, it has to be the entire set. Visually, it's a little confusing having all of these braces and commas sort of stacked up against each other, but if you're careful about it, you can see this is a set that has 8 elements. 1, 2, 3, 4, 5, 6, 7, 8. Some of those elements are sets with multiple elements. Okay, here is one element of the power set. It is a set that has 2 elements. Okay, so notice, as we already mentioned, since the empty set is always a subset of A, it should always be an element of your power set. And finally, let's just wrap it all up and see what we've done. There was a lot in this one. Okay, there's a whole lot of terms, but many of them you've hopefully seen before, like unions, intersections, and probably subsets as well. You've worked with a little bit. Complements are typically very quickly taken in. It's just what is not in the set, as long as you remember that you have to know what the universe is so that you know what's even legitimate to consider as an element to begin with. Product sets are typically a little weird at first, but just remember, don't overthink things. It's not that complicated. It has nothing to do with multiplication. It's just all possible ordered pairs. What's the product set? All possible ordered pairs. That's it. That's all that goes into the product set. All possible ordered pairs where the left element is from the left set and the right element is from the right set. Similarly, power sets can be a bit confusing, but the definition is pretty straightforward. All possible subsets of A. The power set of A is all possible subsets of A. The empty set is always a subset of A, and A is always a subset of itself because they're equal, so I can make this containment in either order. So both of these are always true. Therefore, the empty set always belongs in the power set of A, and the set itself always belongs in the power set of A.